All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Okay, so today we're back at it. Good to hear from you, Chris. We're back at it for the direct stiffness stuff. So this is a follow-up to what we did on Tuesday. So I realized after that this week was a little bit disjointed because we started with direct stiffness, then we hopped back to ANSYS, and then now we're back to direct stiffness. So yeah, probably next time I might do this week a little bit differently, but hopefully you guys still remember what we did on Tuesday. So today we are covering the next element type, which are truss elements. You're going to see that they're quite similar to springs. So there's not too much to talk about in terms of that. What we're going to spend most of our time on today is the discussion of how do we take this and go to 2D problems. So I believe there was a question, I think it was Anas that asked that on Tuesday about rotational degrees of freedom. So we're not there just yet. We'll cover that next week with beams, but we will take this analysis to 2D and we'll see what complications arise from there. Okay. So we aren't going to take this beyond 2D. So 2D is kind of where we're going to stop. Just because again, with the direct stiffness method, this is a pretty big simplification of the finite element method. But I at least want to introduce you guys to all of the I guess a lot of the computations that ANSYS is doing under the hood. So what you're going to see is that going from 1D to 2D does add quite a bit of complexity. We do have to take different directions into account, and that changes how we compute our element stiffness matrix. Going from 2D to 3D is not that much different. It just makes it more tedious, right? So we're going to stop at 2D, but you're going to see there's a lot of interesting things that happen though to the second dimension. Okay. All right. So some announcements. Remember, our midterm project is due this Sunday, so please make sure you guys get that in time. Just because I do want to grade it swiftly, I am placing a hard cap on the midterm project, so please make sure that you get it in before 11:59 p.m. on Sunday. I want to start grading that kind of first thing Monday, and then if people kind of turn it in after that, it kind of messes up the whole thing. So for all the other assignments in this class, well, I guess except for the final project, I am a bit lenient in terms of accepting late work. But for the midterm project, final project, I do have to set hard deadlines on that just because I do want to grade those quickly, just because those are big, big portions of your grade. So I think it's good to kind of grade those quickly, just so that you guys kind of know where you stand. You guys get your feedback so that you can apply it, because this class is going to go very, very quickly. Okay, so please make sure you get that in Sunday, 11:59. If something does happen, you can email me and then we can arrange something at that point. But please try your best to get it in by Sunday, 11:59. Okay. Besides that, the only other assignment is the ANSYS activity 4. So the due date for that will be next Wednesday. So you guys will be able to do that after the midterm project is due. Okay. Beginning of next week, we will also start to discuss the exam. So we do have one in-class exam that's going to be on the Tuesday of week 5. So Tuesday, we will talk about the format of the exam, what to expect. Basically, it's going to be on all of this direct stiffness stuff. And then I will also assign the problem set that's associated with that exam early next week as well. Okay. And so, the thing with 410 is that the end of the class, it is pretty hectic. There's kind of a lot of things that kind of go on. And so, next 2 weeks are going to be pretty busy for us. So just kind of be aware of that. Okay. All right. Any questions before we get started? Our question from the chat: are we allowed to have cheat sheets on the exam? So yes. So on the exam, you're allowed to have one 8.5 by 11 sheet of notes. And so you can write both sides on that sheet of notes. You can write whatever you want. You can type it as well. But yeah, we'll discuss that in more detail next week. But yeah, you can have one sheet of notes with you on the exam. Because I don't provide formulas for you guys. I basically just provide the questions. And so, I let you guys kind of write your own equations and in terms of what you want to bring to the exam. As long as it fits on that one 8.5 by 11 sheet, you can bring it up here. Okay. Any other questions before we begin? Okay, all right, so let's go ahead and get started. Okay, so the topic for today is truss elements. All right, so again, this is building off the discussion that we started on Tuesday about the direct stiffness method. Okay. Okay. So before we start talking about trusses specifically, let's kind of remind ourselves of the direct stiffness methodology or the direct stiffness process. So we're going to use this process for every single direct stiffness problem. The only difference is in the types of elements that we're going to have. Okay. So step one for these problems, if you recall from Tuesday, is the definition or the calculation of the element stiffness matrices. And so based on the geometry, based on the configuration that you're given, you're going to compute the element stiffness matrices for every element that's there. Okay. Step two is assembly of the global linear system. All right, so once you have all the element stiffness matrices, remember we want to solve them all simultaneously in a single linear system. So that's what step two is all about. Step three is to solve it, or excuse me, step three is to apply boundary conditions. And what the boundary conditions do mathematically is that they are going to modify our global linear system. Right? So we've seen kind of both sides of boundary conditions. And so from the ANSYS side, we've seen boundary conditions as kind of the physical representation in terms of what we are modeling. But we're also seeing the mathematical side too, where those boundary conditions actually go in and modify our linear system in order for us to solve for our solution. Okay. Step four is to solve. Now, you can only solve these systems if you have some kind of calculator or MATLAB that's available to you, right? But if you do, then you can go ahead and solve. Okay. And then step five is what I call post-process. Okay. So remember, when you solve your linear system, what you obtain is purely just the primary solution, which in our case is just the deformation. But a lot of times we're also interested in other quantities as well. So things like the stresses, things like the strain. And so you can obtain those during the post-processing step. So we'll talk about that for the first time today as well. Okay. But for the most part, the bulk of the work is going to be in terms of what you guys are doing for these problems are going to be in the first three steps. Okay. Right. And so that's what we're mostly going to be focused on. And for the exam, the first three steps are all you're going to be responsible for, just because you're not going to have access to MATLAB. I know not everyone's graphing calculator can solve a linear system. Plus, it's just kind of pointless to do so. All it does is it just takes up time. And so for the exam, I'm only worried about steps 1, 2, and 3. Okay. And the good news is that out of these three steps, we already have learned everything we need to for steps 2 and 3. Okay. So no matter what type of element that we're using, no matter whether our problem is in 1D or 2D, step 2 and 3 is largely going to be the same, right? So you're going to assemble the same way, you're going to apply boundary conditions in the same way. Okay. So that's why, on Tuesday, I really kind of took my time with this process just because, those are always going to be the same. Okay. What changes depending on the types of elements that you're given and depending on, the dimensionality of your problem, really it's only step 1. So today we're going to learn a new type of element called a truss element, and we're going to see how we compute our element stiffness matrices for those. Okay. But then once you're able to compute the element stiffness matrix, the rest of the process kind of goes in exactly the same way. Okay. So like I said on Tuesday, with these direct stiffness problems, I don't think they're particularly difficult, but they are very, very tedious and they do take a long time. And so, this process here, I guess the good thing for the summer is that, we're only going to be lecturing on these maybe, maybe 3.5 days at most. And so, you're not going to see this. So, if you took this in the regular semester, you'd be seeing this process, ad nauseum for 3 or 4 weeks. And so for us, it's only be 3 or 4 days. So, but this is going to be the same process that you're going to go through. So, the only difference being it's just the element types. Okay. All right. So I want to kind of go over that again, just because, just to kind of show you that, even though we're going over a different element type, our process is not going to change. The only thing that's going to change is how we compute the element stiffness matrices for each particular element. Okay, good. So that was just kind of a review from what we discussed on Tuesday. I wanted to kind of talk about that before we move on. Are there any questions on this process here before we move on to truss elements? Okay, all right. So let's go ahead and talk about the element stiffness matrix for a truss element. Okay. So if you recall from Tuesday, a big part of our lecture on Tuesday was deriving that element stiffness matrix for a spring. Now, the way that that derivation kind of proceeded was that we took our Hooke's law and we kind of generalized it for a case where if we, had 2 degrees of freedom on a spring. Okay. We're going to proceed in a very similar way here. The only difference is that, we have a different governing equation. So instead of Hooke's law, we have actually our general stress strain relationship. Okay. All right, so let's start with a figure of a truss bar. So if you recall from your statics class or you recall from your solid mechanics class, a truss bar is essentially a slender object here that's only designed to sustain tensile and compressive forces. Okay. So that's going to be the main limitation with truss elements is that, we're not going to consider any transverse deformation, any bending deformation. It's only going to be tension and compression along the length of our truss bar. Okay. So to derive our element stiffness matrix, we are going to apply a tensile force on both ends, just like we did with the spring. Right, so we're applying an equal and opposite tensile force on both ends of the truss bar. Okay. And then just like the spring, we're going to characterize this in terms of the deformations of the two ends. Okay? And so if we call the left end, we'll call this node 1, right end, we'll call this node 2. We have D1 that's going along the T direction there, and then D2, which is going to go in that direction there. Okay. Now, before we get to the equations, we do have to characterize the properties of this truss bar. Okay, so our properties are different now. We don't have a spring constant like we had for the spring. Okay, but for a truss bar, we have the following properties. And so on the one hand, we know the length of the truss bar. I guess you could say the starting length or the resting length. Okay, so the resting length of the truss bar is given by L. Okay. We also know some information about the material. So we're also typically given the Young's modulus for the truss bar. right? So remember, Young's modulus is typically given the symbol capital E. The other thing that we also know the cross-sectional area of our truss bar as well. Right, so we'll give that the symbol A, right? So those are our three properties. We have E, A, and L. Okay. All right, so based on this figure, based on the information that's given, we can use this to derive the element stiffness matrix for the truss bar. Okay. Okay, good. Any questions on just the setup for the derivation here about these properties or how we've labeled anything? Okay, all right, so let's continue. All right, so for a truss bar like this, right? So we know that the truss bar is governed by its Young's modulus. And so that basically is telling us that this truss bar is going to follow the rules of linear elasticity. Right? Remember from a couple of weeks ago, we talked about, isotropic linear materials and how their materials behave in terms of stress and strain. Okay. Now, for these materials here, we have basically our linear relationship between stress and strain, right? And so basically for these materials, we have the stress, sigma, is equal to the Young's modulus of the material multiplied by the strain. Okay. So this right here is going to serve as our governing equation. Right? And so from this governing equation, we're going to derive our element stiffness matrix. Okay. So we have this relatively simple equation here. Stress is equal to Young's modulus times strain. All right. So that's fine. That's good. But what we actually want is we want to take this governing equation and express it in terms of the variables that are in our figure here. Okay. So what we're going to do is we're essentially going to be replacing, right? We're going to be plugging in for the stress. We're going to be plugging in for the strain in terms of the variables that we have in our figure here, because that's how we're going to define our element stiffness matrix. Okay, so let's start with the stress. So remember, stress, the way that we define stress is that it is a force distributed over an area. Right, so we know stress has the same units as pressure, right? And so it's force over area. So let's express that expression there, force over area, in terms of the variables that were given in our problem. Okay. Now for this situation here, we're only given one force, right? It's the only force that's being subjected onto our truss bar, which is the tensile force T. Okay. So what we can say is that our sigma is equal to tensile force T, right? And then that force is going to be distributed across the cross-sectional area of the truss bar, which we're also given, which is A. Okay, good. So that was easy, right? And so right away we're given an expression here for sigma that we can plug in for the stress, right? So we can plug in for that. We know T and A, those are given to us in the problem. So our stress is good. Okay. So now let's plug in for an expression for the strain. All right, so let's think about how strain is typically defined. And luckily here, we have a one-dimensional case. And so strain here is actually quite easy to define, right? So the strain, sigma, is equal to, right? So for a one-dimensional kind of system like this, which is, can only change in length, the strain, which is, remember, is a non-dimensional quantity, is the change in length of our structure divided by the original length. Right, our strain represents the relative amount of deformation that we're having. So change in length divided by length. And so luckily for us, we have an expression for change in length, right? Well, first of all, we're given length, right? So length was already given to us in the problem, right? So length is just the resting length of our truss bar. So L is already good, okay? We just have to plug in for the change in length, delta L. So what if we express delta L What if we express delta L in terms of the nodal deformations of nodes 2, 1, and 2, right? So one way we can express delta L is D2 minus D1. Because D2, remember, D2 is the deformation of node 2. So that's how much node 2 is moving to the right from its resting position. And then D1 is the amount that node 1 is moving to the left from its resting position. And so if we take D2 minus D1, that is equivalent to the change in length, right? Makes sense. Right, and so our strain here, we can then express as D2 minus D1 divided by L. All right, so now that we have these, we can just simply plug them in. Okay, so let's go ahead and plug both of these guys into our linear elasticity equation. All right, so we do that. We have sigma, which is T divided by A, is equal to E times the strain, which is D2 minus D1. Okay. Let's do a little bit of housekeeping here. So I'm going to multiply both sides by A so that we have just the tensile force T isolated on the left-hand side. And then what I'm going to do is I'm going to take the product of A times E divided by L and then kind of pull that up front as well, just to kind of make things a bit cleaner. Okay. All right, and so if we do those steps here, we get T is equal to A times E divided by L multiplied by D2 minus D1. So in other words here, we have a relationship between the amount of force, T, that's being applied and the difference in the amount of nodal deformation, D2 minus D1, which is our change in length. Okay, so this equation here, we're almost done. And this derivation I'm going quite a bit faster than last time, just because it's almost the same derivation that you're going to see as a spring. But once we're here, we're basically there. All right, any questions up until this point here? Okay, good. Okay, so now that we have this expression here, we have an expression that relates the tensile force T to the nodal deformations. Okay. Next thing that we're going to do, right? Let me go back up to the figure here, and I apologize. I neglected to write this into the figure at first. But if you recall from the way we set up our springs, not only did we define the deformations at the nodes D1 and D2, we also had defined the forces that were applied on those nodes too. Little f1, little f2. So little f1 and little f2, those are our generic variable names for the for the forces that are being applied. Okay, because remember, ultimately our element stiffness matrix is going to be a relationship between the nodal forces F1, F2, and the nodal deformations D1 and D2. Let me actually write that down. Okay. And it expresses that relationship in matrix form. Okay. Okay. So just like we did with the spring, right? We have this relationship for T. Let's relate T to our nodal forces F1, F2, right? Because this tensile force T is essentially a force that we're applying on both the nodes, right? And so we can say that F1 is equal to minus T and F2 is equal to positive T. So based on the directions, for F1, F2, so based on all those directions, what we have is F1 is equal to minus T, right? Because if we go back up to the figure, F1 is pointing to the right, but T is pointing to the left. And so that means they have opposite sign, okay? And F2 is pointing in the same direction as T at its location. So F2 must be equal to the tensile force T, okay? All right, so now that we have this, we can go ahead and plug in. So let's take this T, our expression for T and plug in here, plug in here. And so what we get is F1 is equal to minus AE divided by L times D2 minus D1. And F2 is equal to positive AE over L, D2 minus D. Okay. I don't know why that L was so funky there. Okay, more than. Okay, so we have our expressions here. So these equations are exactly what we wanted, right? So we have expressions that relate F1 to D1, D2, F2 to D1, D2. Okay, we just have to put this in matrix form. Okay, so distributing the negative, we have F1 is equal to AE over L times D1 minus D2. And then F2 is equal to AE over L times D2 minus D. Okay. And so we put this in matrix form, we get F1, F2 vector is equal to AE over L minus AE over L minus AE over L, AE divided by L times D1, D2. Okay. Because every single D1, D2 has a coefficient of AE over L, just some are positive and some are negative. Okay. Now, of course, that is a little bit cumbersome to write, although that technically is the final answer right there. But typically, it's a bit cumbersome to write AE over L 4 times. But since it's a consistent constant that's applied to every single coefficient there, we can actually factor it out of the matrix just to save us a little bit of writing. So the typical form for the element stiffness matrix for a truss is given by the following. Okay, we have F1, F2 is equal to A times E divided by L times the matrix 1 minus 1 minus 1, 1 times D1, D2. All right, and so what you should notice, and so if you compare this element stiffness matrix to the one for the spring, you'll see that this is almost identical. So the only difference is that for a spring, the spring element stiffness matrix has the exact same form, except instead of AE over L, we have just spring constant, right? So in some ways, the truss and spring are actually quite similar. And in fact, most of the times people can kind of consider them to be one type of element, which makes sense because the way that a truss bar deforms, right? So it can only deform in tension and compression is exactly the same way that a spring can deform, right? So a spring can only be compressed and extended, right? At least in terms of its primary mode diff. I know you can take a spring, you can bend it. I know that's something you can do, but typically, if you're using a spring and it's being used for its intended purpose, it's only going to be in tension and compression, which is kind of what we're doing. And so we can even go a step further. Okay? Sometimes it kind of helps to have this interpretation and so to kind of draw the link between springs and trusses, right? We can look at this combination of variables, this A times E divided by L, which, by the way, are only geometric and material properties of the truss itself. Okay? These can be seen as a kind of like an effective spring constant for the truss bar. Okay. Okay, and so with that, we are going to do an example. But before we jump into that, are there any questions on this? Okay, all right. So let's do a quick example. So this example, should go pretty quickly, but it's just kind of just an illustration of how to apply this. Okay. So for this example, we're going to consider a 3-bar linkage. Right, so we're going to have 3 truss elements, and they're all going to be connected to each other. And just for the sake of simplicity, they're all going to be connected in series so that we have just a purely one-dimensional column. Okay, so our figure looks like the following, right? And so we're going to have 2 walls that are kind of fixing the entire structure here. So to the first wall, we're going to have 1 truss bar that kind of goes like that. We're going to have a node there, another truss bar that's going to be connected to that. Another node there, another truss bar that's connected to another wall on that side as well. Okay, so those are our 3 bars. They're all kind of connected to each other just like that. Okay? Let's go ahead and label them. So the first element will be element A, second will be element B, third will be element C. Okay. We're going to assume that all 3 bars have the same length. And so their length is going to be 30 inches. All right, so elements A and B are going to be made of a material that has a Young's modulus of 30 times 10 to the 6 psi. While element C is going to have a smaller Young's modulus. Okay, so element C is going to have a Young's modulus of 15 times 10 to the 6 psi. We also need their cross-sectional areas, and so for elements A and B are identical, and so they have the same cross-sectional area of 1 inch square. Whereas element C, its cross-sectional area will be 4 times as great, so it'll have a cross-sectional area of 4 inch square. Okay. So that's our system there. So that's our geometry. That's all the properties. We do need our force, right? Otherwise, this structure is not going to be exciting at all. And so we're going to assume that we're going to be applying a force right at the second node. And it's going to have a magnitude of 3,000 pounds. Okay. Oh, I forgot to label the nodes. And so the nodes are going to be labeled 1, 2, 3, 4, going from left to right. So node 1 is going to be fixed at the wall. Node 2 is going to be this one here. Node 3 is the third one down. And node 4 is stuck in the wall on the right. Okay, so for this problem here, what we're interested in is we want to compute. Let's compute all the nodal deformations, so all the deformations for nodes 1, 2, 3, and 4. And then we'll do something new here, right? So something we didn't do on Tuesday. We're also going to compute the reaction forces between the wall and our 3-bar bridge. Okay. So whenever you have a fixed support, there's probably going to be some kind of a reaction force that's being applied there, right? Because remember that we're assuming that this entire structure here is in static equilibrium. Now that's implied, of course, because we have two fixed supports. We have nodes 1 and 4. But from a force balance perspective, there has to be some force, some external force that's being applied onto our entire structure that's going to balance out that 3,000 pounds, right? Because that 3,000 pounds can't just go into nothing. So there has to be something that balances it in order for us to maintain static equilibrium. Okay, so there's our problem. Takes a little bit of time to write everything just because there's a lot of properties to specify. Any questions on just on the setup of the problem? Okay, all right, so let's go ahead and solve. All right, so to solve this problem, we're gonna follow our same methodology that we talked about at the beginning, right? So we're gonna do element stiffness matrices, we're gonna do assembly, boundary conditions, and then solve. Okay, so let's start with the element stiffness matrices first. Now, thankfully, all of these elements here, they're trusses, right? So they're all going to have the same expression for the element stiffness matrix. So let's just write it down here just to remind ourselves, right? So for a truss bar, our element stiffness matrix F1, F2 is equal to A times E divided by L times the matrix 1 minus 1 minus 1, 1 times D1, D2. So basically, for every element that we have, we're going to compute that expression AE over L. And remember, we have to modify the node numbers to match the numbers that our elements are connected to. Okay. All right, so let's start with element A. So the product AE divided by L for element A, let's go ahead and compute that. Right, so A for element A, the cross-sectional area is 1 inch square. The Young's modulus is 30 times 10 to the 6 psi, and our length is 30 inches. Okay. Now you always have to be careful with English units because you have to kind of hope that all of your English units are consistent with each other. Thankfully, everything here is consistent because all the lengths are in inches. But just be aware, sometimes when you're given a length for a problem in English units, it's given to you in feet, and so just make sure you convert that to inches if you need to. Okay, but for the first element here, we have 30 times 10 to the 6 times 1 divided by 30, and so AE over L should just be 10 to the 6th. Okay, so for the element stiffness matrix, then we have F1, F2 is equal to 10 to the 6 times 1 minus 1 minus 1, 1 times D1, D2. Good. All right, so let's do the same thing for element B. So luckily element B, the properties are exactly the same, right? So our AE over L is going to have the same value. The only thing that's different about element B is the node that it's connected to. Okay, so element B is connected to nodes 2 and 3. And so its element stiffness matrix is F2, F3 is equal to 10 to the 6 times 1 minus 1 minus 1, 1 times D2, D. Okay, good. And then finally, element C. Okay, so element C does have different properties, right? So the Young's modulus is less and the cross-sectional area is more. Okay, so let's go ahead and compute those out. So we have AE over L for element C. Okay. So the cross-sectional area for element C was given to us as 4-inch square. Our Young's modulus is 15 times 10 to the 6. The length, thankfully, is the same, which is 30. Okay. So the area and the Young's modulus are, the area is 4 times as much. The Young's modulus is only half. And so that means our AE over L for element C is going to be 2 times that of the previous one. So it'll be 2 times 10 to the 6th. Okay, and so the element stiffness matrix for element C, keeping in mind that element C is connected to nodes 2, 3, and 4. Okay, so we have F3, F4 is equal to 2 times 10 to the 6 times 1 minus 1 minus 1, 1 times D3, D. Okay, good. All right, so those are all our element stiffness matrices. And so in this case, they are pretty straightforward. But again, the trickiest part with these element stiffness matrices is making sure that you got the element numbers, or excuse me, the node numbers correct for each element that you're pointing to. Okay. All right, any questions on the element stiffness matrices? All right, good. Okay, so now that we're done with the element stiffness matrices, let's go ahead and move on to assembly. Or question in the chat. So shouldn't it be 0.5 times 10 to the 6? So for element C, so remember element C, the area is 4-inch square. The Young's modulus is 15 times 10 to the 6. And our length is 30 inches. All right, so we multiply the top, we get 60 times 10 to the 6 divided by 30 inches, which is 2 times 10 to the 6. Oh yeah, area is different for element C. Okay, all right, so let's go ahead and do assembly. Okay. All right, so for assembly, remember, we're going to be constructing our global linear system because we want one linear system that incorporates all of our degrees of freedom. So for nodes 1, 2, 3, and 4. So that means our global linear system here will be 4 by 4. Okay. So let's do this. Actually, let's keep it consistent with the way we have. Okay. Okay, so we're going to start with 4 rows. And so we're going to have F1, F2, F3, F4. And then our matrix portion is going to be a 4 by 4 matrix. Okay. And so just like before, I'm going to go ahead and label the columns. And then the rows are going to be over here as well. Okay, so now we're going to take all 3 of our element stiffness matrices and insert them into our matrix here. Okay. All right, I'm going to do one thing that kind of simplifies things for us first, just because we can see from our element stiffness matrices, right? There's a factor of 10 to the 6 that's always in front. Now, I don't want to have to write that every single time in the global system. So what we can do is we can just factor out that 10 to the 6 from the beginning. So don't be afraid to do this, just to kind of save yourself some writing. And so right away, I'm going to say that, because all the elements have that 10 to the 6 factor, I'm just going to pull that out in front, 10 to the 6. Okay, so what that allows us to do now is that it kind of simplifies the construction of our global linear system. Okay, so we'll just do the same process we did before. Right, so for each element, we're going to take note of which nodes that it's connected to, and then box out that area, and then insert the values into that area. Okay, so for element A we know is connected to nodes 1 and 2. Okay, so that is going to be this portion here. So it's going to be the D1, D2 column and the D1, D2 row. So let's go ahead and put the values in there. So, now that we factored out the 10 to the 6, all that we have in the matrix are just ones. Okay, so 1 minus 1 minus 1, 1. All right, next one on the list is element B. So element B is connected to nodes 2 and 3. That's going to be the second row, third column, second column, third row. I don't know why it said it out of order. It's kind of weird. Okay. All right, so that's that portion right there. And remember, for any part that's overlapping, we're just going to simply add them together. All right, and then finally, we have element C. Element C is nodes 3 and 4. So that's third row, fourth row, third column, fourth column. Which is that portion right there. Okay. Now be careful here. Remember, element C has a slightly different element stiffness matrix. The factor in front was 2 times 10 to the 6. Okay, so everything we're going to add here is going to be multiplied by 2. And then everywhere else that we don't have any values, we're just going to put zeros there. Okay, so we have zeros in all of those portions, right there. Okay, so remember from Tuesday, remember what the zeros mean. So if you have a 0 in your global stiffness matrix, that means that the two nodes that the 0 is connected to, there's no connection in between, right? And so for this instance, we look at this 0 right here, right? So that 0 right there is in the first row in the fourth column. That tells us that there's no connection between node 1 and node 4, right? And that's true, right? So we go back to our figure here. There's no element that directly connects node 1 and node 4, right? And so that 0 there makes sense. Okay, so I'm going to go ahead and simplify this. And so basically wherever we see plus signs, we're just going to add them together. Okay. And so here we're going to have a 2, here we're going to have a 3. All right, good. So this assembly pretty straightforward, just because all the elements are in a line. So we kind of just take that box and just kind of shift it down towards the bottom right. But that's kind of the assembly process once again. Okay. So I'm going to save this, right? So this matrix here, let's save it because we're going to need it to compute the reaction forces. And so next step is going to be the application of the boundary conditions, but I'm going to actually rewrite the matrix after. Okay. All right, but before we do that, are there any questions in terms of how we did the assembly here? Okay. All right, good. Okay, so now let's go ahead and apply our boundary conditions. Okay, so we have three boundary conditions in this case. And so we have a fixed support at node 1, a fixed support at node 4, and a force applied at node 2. Okay, so let's go ahead and apply those. So let me go ahead and rewrite our entire system here. So F1, F2, F3, F4. D1, D2, D3, D. All right, so I'm not going to write the values in just because we're gonna end up overwriting a lot of it anyway. We'll go ahead and fill in everything else that we need at the end. Okay. But let's start with our fixed supports, right? So remember, the way that we apply our fixed supports is that we replace the entire row that's associated with that fixed support, right? So since we have fixed supports applied on node 1 and node 4, that means we're going to modify the first row in the matrix and the last row in the matrix. So let's start with the first row. So the first row, we have 1, 0, 0, 0. Okay. Remember, the way that we apply it is that we apply zeros in every entry in the row that we're applying our fixed support. So on the first row, we have zeros everywhere, except for the entry in the main diagonal, right? So except for the entry where the column matches the row, we're going to put a 1 in that location. And then on the other side for the forcing vector, we're going to put 0 because we're applying a fixed support. And so the value that we're prescribing is actually 0. Okay, and so the exact same thing we're going to apply to node 4. Okay. And so node 4, we're also going to be replacing that entire row, but the main diagonal entry for row 4 is the fourth column. Okay. And so the fourth row is going to look like this. So we're going to have 0, 0, 0, 1. Zeros in every entry except for the main diagonal, which is the fourth column. And then just like before, we're going to set F4 equal to 0. Okay, so those are our fixed supports. Next, let's go ahead and apply our force. Okay, so our force here is being applied on node 2, right? Let's check the direction. So let's go back up to the figure here. So you can see from the figure that the direction for the force is going to the right, which is in a positive x direction. Okay, and so let's go ahead and apply that here. Remember, for a force, the way that we do that is we don't touch the matrix, and so the matrix is left alone. The only place where we apply it is in the forcing vector on the other side of the sum. So for node 2, we're going to go to the second row and apply our 3,000-pound force there. All right, and then for F3, I know I already erased F3. F3, we don't have any boundary condition applied at all, right? So we don't have any forces, we don't have any constraints. And so remember, in those cases, we apply the stress-free boundary condition, which is just 0. Okay, we apply a 0 in the forcing vector, and the matrix we leave unchanged. Okay, so now that we've applied the boundary conditions, the last step is just to fill in all the entries that we still need to for the nodes that don't have a fixed support. Okay, so second row is going to be -1, 2, -1, and then a 0. Okay, and then the third row is going to be 0, -1, 3, -2. Oh, we can't forget. So remember, we factored out that 10 to the 6 from the beginning as well. So remember, don't forget to put that in there. All right, so now we are good. So we've applied all of our boundary conditions. We've assembled everything. Now we're all set to solve, right? But to solve, remember, we're not going to be, we're not actually going to be solving this. And so we're going to be plugging this into MATLAB. Okay. And so when we plug this into MATLAB, and so we plug this into MATLAB and we do the backslash just like we did at the end of class on Tuesday. We get the following results. We get D1 is equal to 0 inches, right? Makes sense because node 1 was at a fixed support, and so it should be 0. Okay. D2 is 0.0018 inches. D3 is 0.0006 inches. And D4, also a fixed support, this was 0 inches. Okay. All right, and so that is our solution. One quick note, and so if you're going to be solving this in MATLAB, so MATLAB sometimes does a poor job of rounding. And so sometimes, you'll solve a system like this, and then you might see that D4 is non-zero, right? And so you might see that D4 is equal to something like 7.99999 times 10 to the minus 18, something like that. Okay? Sometimes. Don't panic when you see this, right? So it may look like a very large number, but if you look at the scientific notation, this is 10 to the minus 18 power, which is essentially 0, right? And so, so if you see something like that, really look at the exponent and, so it happens sometimes when you solve linear systems numerically that just have some rounding errors. But, just make sure you check the exponent just to make sure that it's most of the time it's going to be close to 0. Okay, but yeah, that's the problem. And so, we got to see the entire direct stiffness process here again. You're going to see it many more times through today and through early next week. But that's how it is. Any questions on this so far? Yes.
If the 3,000 pounds was going to the left, would it be negative or you
Exactly.
keep it up?
Yeah. So that's a good point. So the question is, if the 3,000 pound force was it going to the left, we need to adjust for that here as well. So remember, whenever you plug in forces into your forcing vector, you have to assign the sign in order to reflect the direction in which it's being applied to. So yeah, if the 3,000 pound was being applied to the left, we would change this to a negative 3,000. Yeah, good point. Okay, so one last aspect for this example before we go to break. We'll probably take an early break today, just because I don't want to kind of split up the next portion on 2D stuff. We kind of just have to go straight through it. Okay. The last thing I want to do on this example is talk about the reaction forces. Okay. So let's kind of step back to our statics class, step back to our solid mechanics class, and just kind of recall what reaction forces are, right? So reaction forces, these are forces that get applied onto our structure at the location where we are applying constraints. And the main purpose of the reaction forces is to maintain static equilibrium, right? And so, technically, if you go back to all the way back to your physics class, if you're going to have a force that's in static equilibrium, technically the sum of all the forces on the object has to equal 0, right? Now, in the way that we typically kind of formulate our finite element problems, that may not always be obvious, right? So if you look at our structure up here, right? We only see one force that's being applied. We only see that force of 3,000 pounds, right? And so, if you think about it that way, if you think of, we only have just one force in the x direction, technically there's nothing to cancel it out, right? But intuitively, what we know is that when we have fixed supports, right? These fixed supports prevent our entire structure from moving, from having any rigid body motion, okay? But what the finite element kind of process kind of, not that it neglects it, it just doesn't compute it explicitly, is the fact that these constraints are actually applying forces onto our structure in order to enforce that equilibrium. We just don't compute it straightforwardly, when we do these problems in this way. Right? So, but we can compute it, right? So we can actually compute these reaction forces, and we can do it based on our finite element solution. Let me complete the sentence. So reaction force are forces that the constraints apply to our structure to maintain static equilibrium. Okay. Okay, so the way to compute this, right, based on your finite element results, is that you're going to take your deformation solution, right? So the thing that we just computed. Okay. So you can only compute the reaction forces after you fully solve the problem, right? So I would consider this reaction forces to be post-processing, okay? Right, so you're going to take your deformation solution and you're going to multiply it. You're going to do a simple matrix vector multiplication. You're going to multiply it by your global linear system, okay? But the system that you're going to multiply it by is the system that you've made prior to you applying the boundary conditions. Okay. And so if you look back in terms of how we solved this problem, normally when I do these problems, when I apply the boundary conditions, I just wipe over the matrix just because that's the easiest thing to do when you're teaching like this. But for this problem, I took the explicit step where this was our base linear system, and I rewrote it again to apply the boundary conditions. Okay. So to compute the reaction forces, you're going to actually multiply it by this matrix here, right? So this is our global linear system that we obtained right after we did assembly. So we took all of our element stiffness matrices and we just plugged them in. Okay. Okay, and so by doing that, you're essentially going to be plugging in for this vector right here, right? Which is known now. We know what these are, but we just solved them. We just do the simple matrix vector multiplication, and then what we get is a vector of the reaction forces here on the. Okay, so let me just show you what that looks like for this particular problem. Okay, so for this problem, to compute the reaction forces, right? So reaction forces are F1, F2, F3, F4. This is going to be equal to, we have our global linear system before applying the boundary conditions. So this is 10 to the 6 multiplied by 1 minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 3, minus 2, 0, 0, minus 2, and 2. We're going to multiply this by our deformation solution. So basically the solution that we just obtained up here. Okay, so it's going to be a vector where it's going to be 0, 0.0018, 0.0006, and 0. Right, so you don't need any fancy kind of a MATLAB operator for this, and so you just do a matrix vector multiplication. So again, you can do this by hand. I think this is a little bit more reasonable than solving a linear system, but if this is asked of you in a homework, just use MATLAB for it. It's just going to save you a lot of time. Okay. And so we do that for this problem, and what we get is F1 is equal to minus 1,800 pounds. Okay. F2 is equal to 3,000 pounds. F3 is 0 pounds. And F4 is minus 1,200. All right, so first of all, what you see here is that the sum of all of these forces is 0. So that this is one way to kind of do a sanity check for your solution. And so that means that this structure is indeed in static equilibrium. Okay. Next thing you should notice is that F2 is exactly 3,000 pounds, which is what we applied to our system to begin. Okay, so this is our original load. So that makes sense, right? Because that's the force that we applied. But the parts that are interesting here are F1 and F4. Okay? Because remember, these are the nodes where we applied our fixed constraint. Okay? And so this shows that at node 1, we're going to have a reaction force of negative 800 pounds. So that's 1,800 pounds in the left direction. And at node 4, we're going to have a reaction force of 1,200 pounds going in the negative x direction as well. Okay. So that's the exact forces that are being applied at our fixed constraints, and we can actually compute that from finite elements just with a little bit of post processing. Okay, any questions on this example here? Okay, all right, so let's take an early break. So let's take a break. Let's come back at 4:20, and then we'll start talking about 2D problems.
Excuse me, Professor.
What's up?
For the midterm project, there's a portion in the template that says keywords.
Yeah.
What was that for exactly again?
Yeah, so the keywords is it's a standard for scientific publication. It's basically a way to it's basically your Google keywords for people to search your article for.
Oh,
For this one, don't worry about it. I just leave it in as kind of as it's part of a standard template. But for this class, some keywords would be like finite element, ANSYS, maybe the name of your part, like the piston rod or the bearing housing, something like that.
oh, it's like tags.
Exactly.
The
Yeah,
hashtags, no?
yeah, you can think of it like that. Yeah.
All right, cool.
Yeah, don't worry about it too much.
Okay.
Oh yeah. So in the template, I think there's a part at the end of the template where it tells you how to do figures and tables. Yeah, I would prefer the figures and tables to be kind of scattered throughout the text. So don't put them all at the end. The part of the template at the end was just to kind of show you how I want them formatted. There is a little bit of an inconsistency though. So someone pointed out that I think in one part it says to put the table captions above it. I would prefer all the captions to be below. Yeah, so if you're labeling tables and figures, put all of the captions and description below the figure or the table.
Will do. Thank you.
All right, Alicia, so for midterm project, yeah, so so someone kind of asked a similar question in office hours today too. So there's different pistons for different applications, and so different pistons will of course have different loads that it can typically be subjected to. I would say check the size of the piston that was given to you for the project. So if you load up the part inside ANSYS Mechanical or even in any of the CAD softwares like SpaceClaim or Design Modeler, there's a little ruler at the bottom in the middle. So you can use that to kind of get some rough measurements in terms of how long the piston rod is, how wide it is. And so you can use that to kind of say, like what kinds of forces being applied on a piston rod of this length. I think that'll help you narrow down your search. Yeah. Okay, 420, so let's get back at it. Okay, so we just finished our 1D problem for trusses. So you can see here it's very similar to our springs. The only difference is that our spring constant just takes one more equation to compute, it's just AE over L. Now we're going to get into 2D problems. So this is where things start to get pretty interesting. So 2D problems, we can apply this for springs as well, but for our discussion today, we're going to focus on trusses. But just know that everything we're going to talk about in terms of transformation matrices and rotations, they apply to springs as well. Okay. I'm going to go to truss problems in 2D. Okay. So one-dimensional theory for finite elements is it's good, it's fine, it's where you kind of have to start. But we don't live in a one-dimensional world. We live in two-dimensional. We live in a three-dimensional world. But in order to get to 3 dimensions, we have to get to 2D first. Okay. Okay, so we're going to talk about basically how we can modify our methodology, how we can modify our basically our element stiffness matrices to do these problems in 2D. Right, because with the 2D methodology, we'd be able to tackle problems like this, right? So maybe we just have just very simply, two truss bars that are connected in a triangle formation, just like that. Right. So a structure like that, even though a very, very simple structure, we can't handle that right now because all of our theory is in one dimension. Okay. Okay. The challenge that we're going to have here is that, we know that truss bars can only support forces and deformations along its axial length, basically in tension and compression. Right. And so in that way, the orientation of the truss bar kind of dictates the orientation of our coordinate axes, right? But when you have multiple elements that are connected in arbitrary ways, like in the figure above, right? The way that we describe the tension and compression of one truss bar is going to be different than the way that we describe the tension and compression of the other one because they're in different directions, right? And so for the first element here, right, tension is going to be in that direction, but for the second element, tension is going to be in that direction. Okay. So we need to introduce basically a unified way to talk about the deformation and the forces on these truss bars that account for the fact that these can be in different directions. Okay, so we are going to take a little bit of a detour, and so we're going to talk about change of coordinates for a bit. I promise you, it's going to come back. It's going to feel like we're just taking a side quest to nowhere. But I promise you, it's going to come back to Truss eventually. But we do need to talk about coordinate systems and change of variables. Okay. Okay. So first, a couple of definitions. And so let's define a couple of different coordinate systems in terms of what they mean, just so that we can kind of facilitate this discussion. Okay, so the first one we're going to talk about is what I define as the local coordinate system. Okay, so the local coordinate system is, you can think of it as a system that is specific to the orientation of a specific element. Right, so no matter which direction our element is oriented in, we basically match the coordinate system to kind of fit with that orientation. Okay. And specifically for truss bars, our local coordinate system is always such that the tension and compression of the truss bar is always in the local x direction. All right, another thing that I'll note for the local coordinate system, this is just for notation, and make sure you note this down, because we're going to throw these symbols around a lot today. Okay, so for the local coordinate system, we usually define this with a hat. Right, so the local x direction will be x with the little cone hat. Okay. Okay, so just to kind of illustrate, let's say that we have a truss bar that's kind of oriented up at an angle just like that. Okay. The local coordinate system, we're going to basically rotate the coordinate system so that it's aligned with the element itself. Okay. So that means the local x direction is going to go down the length of the truss bar, just like that. Okay. And we're also going to have a local y direction as well. Right, so now that we're in 2D, we have to consider the y direction as well. So the local y direction is going to be perpendicular to that local x direction. Okay, so it's a Cartesian system, a Cartesian coordinate system. All we've done is we just kind of rotated it up to match along with the element itself. Okay. In fact, one thing we can actually do, right, if we draw kind of a horizontal line that's like that, okay, we can define an angle theta, which is the amount that we need to rotate in order to get up to that local coordinate system. Okay, so that's the local system. So the local system is oriented to match the orientation of the element itself. Okay. The other coordinate system that we need is what I call the stationary coordinate system. It's that time of day where the sun comes right through the window and just smacks me in the face for a good 30 minutes. Okay. All right. So for the stationary coordinate system, these are coordinate systems that do not change, hence the name stationary. And they're usually oriented in a way in kind of the standard x, standard y direction. Okay, so for the figure above, we can draw the standard coordinates or the stationary coordinate system. Let me choose a different color for that. Okay. So the stationary coordinate system for this problem above here, or this figure above, our regular x direction would be just in the horizontal line. Okay. And so that would be the x direction in that direction there, and then the y direction would be up here. Okay, so we need a stationary coordinate system because we're going to have multiple different elements that are oriented differently, right? And so the idea of essentially is going to be to transform, right? To transform the element stiffness matrices in each of the elements local systems and transform them to all be in the same stationary coordinate systems. Because once we do that, once we're able to kind of put everything in terms of the same coordinate system, that's when we can do kind of our standard procedure. Okay. Because what happens is if you try to do our standard procedure where you define your element stiffness matrices and you do them in the local coordinates because that's kind of how we've defined them so far, we can't actually assemble them together, right? So the assembly step in our direct stiffness process does assume that all of our element stiffness matrices are defined within the same coordinate system. Okay. So the thing that we're going to do for probably at least the next 30, 40 minutes is to kind of see how we can take vectors and matrices defined in the local coordinate system and transform them into the stationary coordinate system. Okay. Okay, so that's kind of where we're going with this. Okay, so we're going to do a lot of trigonometry, a lot of kind of transformation of variables, and so probably things that you probably thought you'd never see again after those math classes, but you're going to see why it's important in this part. Okay. All right. Any questions on this so far? Okay. All right. So let's kind of begin. Now that we have these two definitions out of the way, let's start to kind of compare them. Okay. So let's consider a situation. Let's consider a vector, just a standard, just two-dimensional vector. So we'll call that vector U vector. Okay. All right, so I'm just going to draw it just like that. It's just a vector in two-dimensional space. It goes in a particular direction. Okay. Now, what I'm also going to do is I'm also going to draw in our two coordinate systems, right? So let's start with the stationary coordinate system. So under the stationary coordinate system, we can express the components of our U vector here in terms of the stationary coordinates, right? And so what does that look like? Remember, to express things in component form, right? What we do is we basically look and see what the coordinates of that vector is relative to the coordinate axis, right? And so this would be ux, and this would be uy, right? And so what we can say is that U vector is equal to ux and uy, right? Essentially the xy coordinates of that vector, which is where that vector, how far that vector proceeds along the standard x direction, the standard x-axis, and the standard y. Okay. Let's take that exact same vector and attempt to draw it exactly the same way. So that's not bad. Okay. So let's take the same vector. Okay. So the vector itself is not changing, right? So that's the important point I want to make. So the vector itself is exactly the same. Okay. The only thing that's going to change is how we describe that vector, right? So in one sense, we're going to describe the vector in terms of its standard x, y. We're also going to describe the vector in terms of a local coordinate system, okay? So the local coordinate system, may not necessarily align with the vector itself. So actually for this purposes, it's not going to, okay? So let's define a local coordinate system, maybe something like this. Right, so we have x hat, y hat, where, again, the way that we obtain this this local coordinate system, we just rotate it counterclockwise up by an amount theta, okay? We can describe this exact same vector in terms of its components in this rotated system, okay? So this would be ux hat and uy hat. Okay? In other words, we can find that u vector is equal to ux hat, uy hat. Right, but it's the exact same, I want to emphasize it's the exact same vector. You can think of it as, you're looking at the same object just from a different perspective, right? So with the pen, right? So if you look at this pen, right, it's going to look this way if you look at it from this perspective. But if you look at it like this, it's going to have a different, different perspective, a different way that you're going to see it, right? But it's the same pen, right? And so it's the same idea here where, we have the same vector, we're just describing in terms of different coordinate systems, okay? But, because it's the same vector, these two descriptions should technically be the same, right? Because it's the same vector. So what we can do is we can say, right? You just simply equate them together. Oh, my friend's calling. Scan likely. Okay. So let's go ahead and equate these together. Right, so we have ux, uy is equal to ux hat, uy hat. Okay. But that form itself is not that useful, or we can't really do anything with this. So, another way, so you've probably seen this form before in one of your previous classes, and you might have thought, why does this form exist? So we can do this, we can express this in terms of the unit vectors in each of the directions. Okay. Okay, so another way we can express this is ux times I plus uy times j is equal to ux hat I hat plus uy hat j hat. Okay. Where I and j, okay, I and j are unit vectors that go in the stationary x and stationary y directions respectively. And then I hat and j hat, these are unit vectors that go in the local x and local y directions. Okay. So this is just another way that you can express the components of a vector, right? So you basically just take the vector component, you multiply it by a unit vector in that direction, and you just add it to the other components multiplied by the respective unit vectors as well. Okay. Okay, so let me kind of illustrate these I hat, j hat vectors. Okay. Okay. So let's do I and j first, right? So the I vector is basically a unit vector that goes in that positive x direction. J is a vector that goes in that direction. Okay? And they are unit vectors, and so unit vector means that they have a length of just one. Okay? And then I hat and j hat, I should not have chosen hot pink. Which is this one. Okay. So I hat is a unit vector that goes in the x hat direction. J hat is a vector that goes in the y hat direction. Okay. So that's all that is. But the nice thing about this form of the equation here is that we actually have kind of an algebraic equation that we can actually solve for. Okay. And so what we're actually going to do is that we're actually going to be plugging in for the unit vectors just to get a relationship, because we want to get a relationship between ux, uy, and ux hat, uy hat. Okay. So the way that we're going to do that is we're going to plug in, or we're going to express the unit vectors in terms of its corresponding pair. So we're basically going to plug in for I and j and express that in terms of I hat and j hat. Okay. Which sounds a bit complicated, but trust me, it's less than what. Okay, but just wanted to get those kind of definitions out of the way. So I know it's pretty dry and kind of definition heavy now, but and it's still going to continue like that for the next 20 minutes or so. But just bear with me. I promise. We're going to get back to we're going to get back to finite elements pretty soon. But up until this point, are there any questions on just how these different systems are defined or how the vectors are defined? Okay. Okay, so let's go ahead and get started. So first thing we're going to do is let's express the I vector in terms of I hat and j hat. Okay. All right, so to do that, we're going to use some trigonometry here. So let's draw I. Okay, so remember, I is a vector that goes in the stationary x direction, so it's going to be perfectly horizontal. Okay. And then what we're going to do here is we're going to basically express the components of I in terms of the local coordinate systems. Okay. So I'm going to draw these two other vectors here. I'm going to draw this A hat vector. Okay. And then a B hat vector. Right angle here. Where this A hat vector and B hat vectors are defined such that they match our local I hat and j hat direction. Okay. And then we also know that angle there as well, right? Because we know exactly how much we rotate, right? You can think of that angle as, how much we rotate away from the positive x, the stationary x direction. Okay. All right, so what we can do here is that, since we have a right triangle, we have an angle that we know, we can basically use some trigonometry, some sines and cosines to express, each of the different lengths of this triangle here. Okay. So for instance, right, we know that A hat, the length of A hat is equal to the length of I, which is the hypotenuse, multiplied by cosine of the angle theta. Right? right? So that's just trigonometry there. Okay. In a similar way, we can express the length of the b hat vector is equal to I, the hypotenuse, multiplied by sine of theta. We can simplify this a bit, right? Because we know that I is a unit vector, right? And so the magnitude of I is just going to be 1. Okay. So now we have the lengths of two of those sides, right? So we know the length of A hat and we know the length of B hat. Okay. Okay. So now that we know the lengths of those two vectors, let's just use simple vector addition in order to add them together, right? Because if you look in terms of how I constructed this triangle, right? Okay. And so if we want to arrive at this location here, right? So that's kind of the endpoint for both paths, right? One way that we can get to that location is we can just simply follow along the I direction. Okay. Right. Another way that we can get to that location is we can just simply travel along the A hat direction and then travel along the B hat direction. Okay. Okay, so in other words, what we can say is that I, the vector I is equal to A hat not the magnitude, just the vector itself. I is equal to A hat minus B hat. We put that minus sign there just because we're going in the negative J hat direction. Okay. Right. And so we know exactly kind of what the A hat and B hat vectors are. Okay, so let's go ahead and plug in the magnitudes for that. Because we have I hat is equal to cosine of theta multiplied by I hat minus sine theta multiplied by J hat. All right, so we use a little bit of trigonometry, a little bit of vector algebra there to kind of get this result, right? So essentially what we have now is that we have this expression I is equal to cosine theta I hat minus sine theta J hat, okay? And we can go back into this equation here and we can plug that in for I, just like that, okay? So essentially we'll have eliminated that I variable because then now both sides of the equation will be in terms of I hat and J hat, okay? We're going to do the same thing. We need to do the same thing for for the J vector here, which we'll do soon. But we're going to do basically the exact same thing with trigonometry and some vector algebra. Okay. Okay. Any questions in terms of how we got this expression here? Okay. All right. So let's do the same thing. Let's do the same thing with the J vector. Right, so we're going to express the J vector in terms of I hat and J hat. Okay. Okay, so let's start the same way. So let's go ahead and draw the J vector. So the J vector is a vertical vector because it's going in the stationary Y direction. Okay. And then just like we did before, we're going to make a triangle based on the directions of our local coordinate vectors. Okay, so once again, we're going to have a B vector, B hat, and A vector, A hat. You have a right triangle in between them, and then an angle theta, just like that. It's a little messy. A hat. Okay. All right, so let's do the same things we did before. Okay. So let's first find the lengths of the side. So let's find the length of the B hat vector and the length of the A hat vector. Okay. So the length of the A hat vector is equal to J multiplied by sine theta. and the length of the b hat vector is equal to length of j cosine theta. Just based on the trigonometry of the system. Okay. All right, and just like before, the j vector we know is a unit vector, so that has length 1, right? So that essentially cancels out. And then once again, we can then just use some vector math. And so j in this case is equal to b hat plus a hat. Okay. So in other words, j is equal to sine theta I hat plus cosine theta j hat. Okay, so now we have expressions for both I vector and j vector, and so now we can plug this back into this expression up here. Okay, it's going to take a little bit of algebra, but essentially what we're going to get from this is we're going to get an algebraic relationship between ux uy and ux hat uy hat. Okay, and so what that's going to do is that's going to be valuable because then we can use that to express our element stiffness matrices in the stationary coordinate system, okay, which is ultimately what we. Okay, so let's go ahead and do that. Okay, so let's plug both of these into our equation above. Okay. Okay, so let's do that. We get ux, right? Originally, ux was multiplied by I vector, and so we're going to plug in for I vector now. Okay, so it's the ux multiplied by cosine theta I hat minus sine theta j hat plus uy multiplied by j vector. And so j vector we're going to plug in with the expression that we still have on the screen there. Sine theta I hat plus cosine theta j hat. Okay. All that's equal to ux hat I hat plus uy hat j hat. Okay. For this expression here in parentheses, this is the original I. In this expression here, this is the original j. Okay. Okay, good. All right, so we've essentially eliminated those variables, which is good. Okay. Next thing we're gonna do is we're gonna do a little bit of algebraic kind of manipulation here. So we're gonna take the left-hand side of this equation and we're going to group the terms together. Okay. And we're gonna group them according to terms that are multiplied by I hat and terms that are multiplied by j hat. Okay. All right, so it's just moving some terms around. And so it's basically just kind of doing a little bit of distribution, a little bit of kind of, moving things around and just kind of grouping them together. Okay. Okay, so we do that. And what we get is ux cosine theta plus uy sine theta. Okay. Those are the I hat terms. Plus, we have a minus ux sine theta plus uy cosine theta. Those are the j hat terms. Okay. And that's equal to ux hat I hat plus uy hat j hat. Okay. Okay. Almost done with this derivation. I promise you. There's just one more step. Okay. Done with this derivation, and then we actually have to use it to transform our element stiffness matrix. So that's a bit more time as well. What I'm hoping is that we get done with this derivation and we can do at least one example today. I don't think we'll get through everything in Truss equations today. Typically, it takes a while first time we go through it. But we'll finish this up on Tuesday for sure. Okay. All right. So now that we've grouped it, we can basically set these terms equal to each other, right? Because if we look, this term in green is multiplied by I hat, and on the right hand side we have ux hat. Okay. And so what we can do is we can say ux cosine theta plus uy sine theta is equal to ux hat. Okay. So that's the algebraic equation that we obtained by equating the I hat terms. Okay. And then we get another algebraic equation from equating the j hat terms. Okay. And so we equate those two sides equal to each other, we get minus ux sine theta plus y cosine theta is equal to uy hat. All right, so we have two equations. Okay. We're going to do the favorite thing that we always do when we have two equations like this. We're going to put it in matrix form. Because if we look at the left-hand side of this equal sign, we have ux and uy, and they're just multiplied by sine or cosine. Okay. And so we do that, we get the matrix cosine theta, sine theta, minus sine theta, cosine theta, multiplied by ux, uy is equal to ux hat, uy. All right, so all that work, all that half an hour of just looking at triangles and angles and doing algebraic manipulations, what did we get from all that? Okay. So the main thing that we got from that is actually this matrix here. So this matrix, which is just a matrix of sines and cosines, we call this the transformation matrix. And it does one very powerful thing for us, right? And so if you look at the structure of this entire system here, right? Not just the matrix, but you look at the vectors, right? On the left-hand side, we're multiplying the transformation matrix by ux and uy, which are the vector components in the stationary coordinates, okay? And then by doing so, what we obtain is the same, the components for the same vector, but in the local coordinates, okay? So what this transformation matrix essentially does is that by multiplying our component vectors by this transformation matrix, we can go very easily between the stationary coordinate system and the local coordinate systems. Which is exactly what we want, right? So we want kind of an easy mathematical way for us to go between the two coordinate systems, okay? Now, we're not done yet, right? So the next step is like I said, to apply this to our element stiffness matrix, but this is going to be an essential step in that process, okay? Because we're going to take our element stiffness matrix and basically apply this to our vectors, and then we're going to get our system from there. Okay. Any questions up until this point here? Okay, good. All right, we're making good time. Okay. Okay, so let's kind of put this in our back pocket and let's go back to the element stiffness matrix for a truss. Okay. Right, and I'm actually going to express the truss element in terms of the local coordinates because we're kind of that's kind of what we said from the beginning, right? Okay, so for our truss bar, what we have is F1 hat, F2 hat is equal to AE divided by L times 1 minus 1 minus 1, 1 times D1 hat, D2 hat. Okay. Where, and let me actually illustrate it, that might be a little bit easier. Okay, so this is for a situation where we have a truss bar, it's oriented kind of arbitrarily, okay? Remember, the local x direction is along the length of the element itself, that's how we define it, and the y direction is up that way. Right, so right now this element stiffness matrix is only calibrated for this coordinate system that's local to the element itself. Okay. In fact, we can actually take this a step further, right? So if you look at this expression up here, right, we know that in the local coordinate system, all of the forces and all of the deformations are going to be in that x direction, right? So we actually don't have anything in the y direction. And so we can kind of revise this. And so instead of having F1 hat, we can have F1 x hat. F2x hat, D1x hat, D2x hat, okay? Because these are all going in that local x direction. Okay. So next thing we're going to do, and this step it kind of comes out in left field, is that we need to kind of expand these vectors and expand these matrices to include that local y direction. Okay. Okay. So before we didn't need it because we were looking at 1D problems and it was impossible for a truss bar to deform in a direction that's perpendicular to it. Okay. But since now we're tackling two-dimensional problems, we have to account for every single kind of component in that second dimension. Okay. And so we're going to expand this. And this part's a little bit strange because we're going to add a bunch of zeros because mathematically we don't want to change the expression of what we have above. We essentially just need to make a slot for it. Okay. All right. So what does that look like? And so instead of having F1x hat, F2x hat, we have to add F1y hat, F2y hat as well. So it actually makes our system bigger. And so instead of being a 2x2 system, we're now going to have a 4x4 system. All right. So we're going to have F1x hat, F1y hat, F2x hat, F2y hat. Okay. This is equal to, we still have AE over L on the right hand side, okay, outside the matrix. And actually, let me do this first. Let me put in the deformation vector here too. Okay. So a deformation vector also we need to include that local y direction. So we have D1x hat, D1y hat, D2x hat, D2y. Okay, so we've expanded this to include that y direction, but just because we expanded it doesn't mean that we expect to have deformation in those directions. We're essentially just making slots for it so that we can transform them basically. Okay. And so our matrix here is going to be a 4x4, but the only non-zero entries are still going to correspond only to these degrees of freedom that we have in our original element stiffness matrix. Okay. And so that means we're going to have 1 here, a 0, -1, 0. Okay. So for every row or column that's associated with a y, we're going to have a 0. So that means the entire second row is going to be zeros, okay? Because that's the row that's associated with D1y. Okay. Third row is going to be -1, 0, 1, 0. And then last row is going to be 0, 0, 0. So again, that last row, oops, sorry. Okay, so that last row there is again associated with D2y, and so that's why that entire row is going to be zeros. Okay. Okay, so we didn't change the element stiffness matrix at all yet. We haven't applied the transformation, but all we did was we opened up slots for the y components. Okay. Okay, good. All right, so now that we've expanded this, now we are ready to transform, right? Because right now, everything is in terms of the local coordinates, but we want to apply our transformations so that we can have everything in terms of the stationary coordinates instead, okay? And so where that's going to happen is that we're essentially going to plug in for this vector here and this vector here, okay? So we're going to use our transformation matrix. The transformation matrix with the sines and the cosines. We're going to use that to basically transform every vector component with a hat into the stationary coordinates. Okay. Okay, good. All right, any questions on any of this so far? Okay, good. Okay, so let's go back to our transformation matrix and let's kind of remind ourselves what that looks like. Okay. And so basically, if we have a vector in the local coordinates, right? Ux, y hat, uy hat, right? That's equal to the corresponding components in the stationary coordinates multiplied by the transformation matrix. Okay. So let's go ahead and set that up. And so we need to set up two transformation matrices. One for node 1, the other one for node 2. Okay, so I'm gonna do this just for the forces, but just know that it applies for the deformation as well. Okay, so we have F1x hat, F1y hat is equal to transformation matrix. I'm going to use shorthand notation here just because we're going to write a lot of sine and cosines. Okay. And so if you see a C is equal to cosine theta. And then I'm going to use an S is going to equal to sine theta. Okay. So just kind of keep that in mind. Okay, so I'm just going to use C's and S's from now on. Okay, so F1x hat, F1y hat is equal to C times S, or C, and then S, and then minus S, C. Okay. This is multiplied by the corresponding components of this vector in the stationary coordinates. So F1x without a hat, F1y without a hat. Okay. And then we're going to do the same thing for node 2. So node 2 is going to be f2x hat, f2y hat is equal to c s minus s c times f2x no hat, f2y no hat. Okay. Okay. All right, so those are the two transformations that we need to do, okay? So that makes sense. The only problem is that if you look at our element stiffness matrix right now, we have kind of a combined thing going on here, right? So F1x, F1y hat, F2x hat, F2y hat, they're all kind of stacked on top of each other, okay? So let's make a combined transformation matrix that accounts for both of these together. Okay, so you combine these into one, we get the following. So we get F1x hat, F1y hat, F2x hat, F2y hat is equal to. In order for this to be linearly algebraically consistent, I don't know another way to say it, right? In order for this to be kind of good, we need to multiply this by a 4x4 matrix instead, right? And so on the right here is going to be F1x, F1y, F2x, F2y. Okay. Okay, so we're basically going to take these 2x2 transformation matrices and you can kind of think of it as kind of like assembly into this kind of bigger one here, right? Okay, so for this one here, right? This is kind of the combination of, the node 1, right? So that's going to be in this portion right here. Okay. That's going to be C, S minus S, C. Meanwhile, this one, the other one is going to be for node 2. So that's going to go right down here. Okay. All right, so you have C, S minus S, C. Okay. And then we're going to have zeros everywhere else. All right, we're almost done. I promise. We're almost done with the derivation. It always takes a while. Okay. So this is really good, right? And trust me when I say this is really good. Okay. Because what we can do now is that now we have something we can plug into directly into our element stiffness matrix up here, right? And so basically we can take this entire thing here and plug that in to this right here, right? And that accomplishes our goal exactly, because then in that point we eliminate all of the local coordinates from our system, and everything is going to be in terms of the stationary coordinates, which is exactly what we want. Okay, we can do the exact same thing. We can do the exact same thing for this matrix or this vector on that side there, right? So we're going to have the exact same transformation matrix, so this exact same 4x4 that we just looked at just now, okay, and apply to those ones there. So we'll have eliminated all of the local coordinates. The only caveat is that now we have these gigantic transformation matrices around, but those are actually very easy to do. Okay, okay, so let's go ahead and plug this in. The element stiffness matrix. Okay, and so we do that. It's going to be a lot of writing here, but it'll be worth it. Okay. All right, and so on the left-hand side, we're going to plug in for the F hats. And so F1x hat, F1y hat, F2x hat, F2y hat. Okay. And so first we have a 4x4 matrix. And so we have C, S minus SC 0, 0, 0, 0, 0, 0, 0, 0, CS minus SC. All that is multiplied by a vector of the forces in the stationary coordinates. So F1x, F1y, F2x, F2y. Okay. Right, so this combination together used to be F1x hat, F1y hat, F2x hat, F2y hat. Okay, so all we did was we just plugged in for that. Okay. Next to that, we have our element stiffness matrix, and so we have A times E divided by L, okay, which is then multiplied by 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay, so that part did not change, right? So that's just a matrix of just our geometric and material properties, and so that's going to be the same no matter what coordinate system we're in. Okay, just because you look at a thing from a different perspective, it doesn't change from aluminum to bronze, right? It still has the same Young's modulus. Okay. And then from there, we're going to multiply it by the vector of our deformation, which we're going to apply the exact same transformation to. Okay. All right. So this is multiplied by exact same transformation matrix. So we have C S 0, 0 minus S C 0, 0, 0, 0 C S 0, 0 minus S C. And then this is multiplied by a vector of the deformations in the stationary coordinates. So D1x, D1y, D2x, D2y. Where this combination of the transformation matrix and the vectors, this used to be D1x hat, D1y hat, D2x hat, D2y hat. Okay. Good. So everything or every vector quantity now is in terms of the stationary coordinates. So that's good, right? That's what we want. That was kind of the goal here. So we've taken our 2D scenario, we're kind of divorced ourselves from the local coordinates. Now we have everything in terms of the stationary coordinates. No more hats. Okay, but we're not done just yet, and so there is a bit more algebra that we have to do. Okay. Because having these ginormous transformation matrices kind of floating around is a little bit unsightly. Okay. And so what we're going to do now is all we have to do now is we just have to simplify. Okay. And the way we're going to simplify is that we're basically going to be multiplying all of these matrices together in order to get one single element stiffness matrix. Okay. And that's the matrix you're going to be using for your problems. Okay. So we're simply just going to be performing just matrix multiplication, right? So it is tedious, right? So don't get me wrong. Multiplying two 4x4 matrices together is not how I typically want to spend a Sunday afternoon. Okay. But this is something that you can kind of automate with that. Okay. And one nice thing here too, and I kind of almost always gloss over this fact, right? We do have to move this matrix here on the left-hand side. We have to multiply it over to the right. Okay. normally when you do this, normally when you kind of move a matrix from one side of the equation to another, right? If you remember from your linear algebra class, that involves multiplying by inverse, which, if there's anything that's more annoying than doing matrix multiplications, finding a matrix inverse, especially for a 4x4 matrix. Okay. But we're in luck because, these transformation matrices that we have here, they have the property where the inverse of the matrix is actually just the transpose, right? So you just have to take the transpose of the matrix. That gives you the inverse. Okay. Okay. So I'll just mention it. We're not actually going to go through and multiply. I think we've done enough derivations for today. I do want to get through one more example today. Okay. But if you do all that kind of algebra there, you kind of you multiply it out, you take the transpose, you multiply those 4x4 matrices, you finally obtain the element stiffness matrix that we've been kind of coveting this entire time. Okay. So this expression right here, this is going to be the element stiffness matrix that you're going to use for 2D truss and 2D spring problems. Okay, so it looks like the following. So we still have our vector of forces here. Now these forces are in the stationary coordinates. We have F1x, F1y, 2x, F2y. Okay. This is equal to A times E divided by L. Okay, so that factor there just kind of is just along for the ride the entire time. Okay. Then we have this matrix that is going to involve a lot of sines and cosines. Okay, so the matrix is the following. So we have cosine squared, cosine times sine, minus cosine squared, minus cosine sine. Okay. So that's the first row. That's the only row that I'm going to write in its entirety. Okay. Next row, we're going to start right at the diagonal. Okay, so next row is going to start s squared minus cosine sine minus sine squared. Okay. And you'll see in a second why I skipped that first entry, right? It's kind of more for ease of writing later. All right, so for the third row, we're going to start with the third column. So it's going to be cosine squared, cosine times sine. And then for the last row, we're only gonna define the entry that's in the last column. Okay, so this is sine squared. And this is multiplied by the vector of our deformations in the stationary coordinates. Okay? So d1x, d1y, d2x, d2y. Okay, all that work and we arrive at this expression right here. Okay, so I know it's a very long derivation. I usually don't like to do hour-long derivations for things, but I think it's important to kind of understand where the context from all these sines and cosines have come from. Okay, and so we could have just skipped all that. We could have just started with this, but I think it's important to kind of see where, first of all, where all these sines and cosines coming from, and kind of really understand kind of the challenge that we're working with in 2 dimensions. Okay. Because once you go to 3 dimensions, the challenges are the same, right? And so you still have to come up with a stationary coordinate system where you can combine all these things. So that doesn't change. Of course, just the complexity changes because you're in 3 dimensions. But we do a lot of these same things. And ANSYS is doing a lot of these things kind of underneath the hood for you to account for different orientations of elements and the multiples. Okay. Okay. So anyway, back to this matrix here. So the reason I only define just the upper right portion is that this matrix here is actually symmetrical. And so you'll see that when we actually do these problems, I'm actually only going to do the calculations for this upper right portion. And then for everything else, I'm just going to fill in based on the symmetry of the matrix, just to kind of save you some calculated time. Okay. It doesn't cut it in half, unfortunately, just because that main diagonal, we do have to compute it. But it does save you a significant amount of time. So just so that you don't have to compute those lower six entries. Okay. Okay. Finally, and so now we can finally do an example. Are there any questions before we jump into our example? Okay, all right. So let's go ahead and do an example. Okay, so our first 2D example here. Okay. So let's put that knowledge to use and let's look at this 3-bar assemblage. I guess technically 2 bars and 1 spring. Okay. Okay. Okay, so our truss bars look like the following. So first we have a vertical one. Just like that. Okay, so we'll call this element A. We have a horizontal bar. It's like this. Call this element C. And then we have a spring that's also attached to this. We'll call that element B. Okay, and then so we need to add some constraints here. And so we actually have a bunch of fixed constraints. And so we have a fixed constraint up on the upper part of element A. We have a fixed constraint for the spring. Okay, so that's fixed on the other end there. And we actually have a fixed constraint for element C as well. Okay. We actually have 4 fixed supports. Okay. Let's label our nodes here. So we have node 1 is going to be the point where they all converge together. Node number 2 is going to be the fixed support for element A. Node 3 is going to be the fixed support for the spring B. And then node 4 is going to be the fixed support for element C. All right, and then we do have a force here as well, right? We need to have a load, otherwise we're not going to be able to measure anything. And so let's say we have a downward force of 10,000 pounds being applied at node. Okay. Oh, sorry, one more thing that we need. So we also need to know the orientations of these elements, okay? So element C, we're going to assume is perfectly horizontal, okay? Element A is going to be perfectly vertical. And then element B, we're going to assume is angled upwards at an angle of 45 degrees. And then just to be complete, from element B up into element A is another 45 degrees. So element A you can consider as 90 degrees. Okay, so let's also write in our element properties. And so for elements A and C, right, so these are truss bars, and so we need to have their Young's moduli, the cross-sectional area, as well as the length. The Young's modulus in this case is 30 times 10 to the 6 psi. The cross-sectional area we're assuming is 2-inch square, and the length of those two elements is going to be 10 feet. For element B, we have a spring, and so the only constant that's relevant for a spring is its spring constant. Okay. And so the spring constant for element B is 250,000 pounds per. Okay, and so for this problem, what we want to do is we want to compute. We only have one node here that's free, right? So every other node is fixed. right? And so we want to find out how much node 1 is going to deform in response to this swim. Okay, so we have kind of our standard direct stiffness problem here. The only difference now is that we are in 2D. Okay, but what you're going to see is that we're going to follow the exact same process that we followed as the first example we did today. The only difference now is that our element stiffness matrices are much bigger than we were. Okay, so 2D problems, there's nothing inherently more complex about them. They just take a lot longer just because the matrices are just bigger. Okay, but we're going to follow the exact same process of element stiffness matrix, assembly, boundary conditions, solution. Okay, so let's start with the element stiffness matrices. So just like we did before, we're going to go element by element and then compute its element stiffness matrix. Okay. Okay, so for 2D problems, what I always like to do is that I like to pre-compute the sines and cosines because, you can see from our element stiffness matrix here, it's mostly going to be a combination of sines and cosines. And so if you can pre-compute them, it actually makes filling out the matrix a lot simpler. Okay. Because if you don't pre-compute it, not that it's particularly challenging. So I will say that for these problems, I'm not going to give you an exotic angle, and so I'm not going to give you like 63 degrees or something like that, or 67 degrees or something like that, right? And so I'm always going to give you something that's either 0 degrees, 90 degrees, 45 degrees. Occasionally, I'll give you something like 30 degrees or 60 degrees, just because those are also pretty standard. But it still helps to kind of pre-compute these beforehand, just so that you know what to plug in. Okay. So let's go to element A first. Okay. So element A is a vertical element, right? And so if you measure the amount of angle that we need to rotate in order to get into that orientation based from the horizontal, we're rotating up 90 degrees, right? So for a vertical element like this, the theta is 90. Okay. Now that helps us out a lot because 90 degrees is a nice orientation, right? Because what do we know? Cosine of 90 degrees is what? 0, right? Sine of 90 degrees is 1. So when we go and plug into our element stiffness matrix, every term or every expression that has a cosine, we're just going to know it's 0 automatically, just because 0 multiplied by anything else is 0. Okay. And even the terms with sine are just 1. So we actually end up pretty nice. Okay. So let me write down the expression for the element stiffness matrix one more time here. Okay, so for element A is connected to nodes 1 and 2. So this is going to be F1x, F2, or F1y, F2x, F2y, okay, is equal to A times E divided by L multiplied by, we have cosine squared, cosine times sine, minus cosine squared, minus cosine sine. The next row we have sine squared minus cosine sine minus sine squared. Third row, we have cosine squared, sine times sine. Last row, we have just sine squared. And we know that this entire thing is symmetric, okay? And this is multiplied by the deformation vector. So d1x, d1y, d2x, d2y. Okay, so that's what we're going to plug into. Okay. And like we said, anything with a cosine, we're just going to set that equal to 0. Okay, so that means the entire first row, right? So if you look at the entire first row there, everything has at least one cosine. So cosine squared, cosine times sine, minus cosine squared, minus cosine sine, they all have cosine. So that entire first row is going to be 0 because our orientation here is 90 degrees. Okay. Let's also compute AE over L as well. So let's see. And actually both trusses are the same, so we can just kind of pre-compute that up here, right? Okay, so AE divided by L, we have 30 times 10 to the 6 times 2 divided by 10, okay? Now be careful, okay? So this length here is given to us in feet, and so what we actually want, because everything else here is in inches. Our area is in inches squared. Our Young's modulus is pound per inch square. Okay, so that means we need our length to be in inches as well. Okay. Okay, and so we plug that in, we get 5 times 10 to the 5th. Okay. Pound per inch. Okay, so that means our element stiffness matrix for element A is going to be 5 times 10 to the 5th. Okay, so that factor is out in front. Let me go ahead and write in the force vector as well. X, F1y, F2x, F2y. Okay. Okay. So outside the matrix, we have 5 times 10 to the 5th. Inside the matrix, that entire first row is 0. Very nice, because everything in that first row has a cosine. And then we have our deformation vector as well. All right. So before we move on to the second row, right, we're going to take advantage of the symmetry that we have in this matrix, right? So remember, the reason I only define the upper right portion is that it's symmetric with the bottom part, right? And so one way to take advantage of this is that every time you write a row in the element stiffness matrix, you can write that exact same row into the column, okay? So you're basically going to take that row and you're going to transpose it down, okay? So what that means is that every time you write an entry, you're going to rotate that into the corresponding value in the column as well, okay? So since that second entry was 0, that means that entry is going to be 0 as well, okay? The third entry in that row is third entry in that row is 0. That means the third entry in the column, the first column is going to be 0 as well. Okay. The fourth entry in that row is 0. That means the fourth entry in the first column is also going to be 0 as well. Okay. So not the best example of this because everything was 0 there, but you're going to see me repeat the same trick for all the other rows in the system as well. Okay. So that's kind of your trick. And so that's, a big part of the section is, recognizing that, yes, there is a lot of writing that has to be done. These matrices are ginormous, but whatever shortcuts and whatever kind of tricks that you can use to kind of make sure that you're consistent in all your calculations, take advantage of everything, okay? And so one of them is, taking advantage of the symmetry of our element stiffness matrix. Every time you write a row, you just write that into the column as well, okay? So row, column, okay? Let me demonstrate with the second row. Okay, so second row in the matrix, we start with sine squared. Okay, so that's our first non-zero entry. Okay. Right, so sine in this case is 1. So 1 squared is just 1. Okay. Next, we have minus cosine sine. That term involves a cosine, so that one's going to be 0. Okay. And next we have minus sine squared, which is just a minus 1. Because we have minus times 1 squared. The minus is actually outside the square, right? And so, just kind of be careful about that. And so we have 1 squared, which is 1 times minus 1, which is minus 1. Okay, so let's do the same trick that we did before, right? So we have less entries to do this with, so we only have 2. But let's write all the entries that we wrote in this row and just rotate them down into the corresponding column. Okay, so first we have this 0 here. Okay. So that's going to rotate down and become a 0 right here. Okay. And then we have this minus 1. That's going to rotate down into the last entry of the second column. Okay. And that's going to be a minus 1, just like that. Okay, good. All right, so let's go ahead and continue onwards. And so for the last 2 rows, it's pretty simple because we've already written in most of the entries here. So for the third row, both of those terms, cosine squared and cosine sine, both of them involve cosine. Okay. So both of those are going to be 0. Once again, let's do our trick. And so we have the last entry in the third row. Let's rotate that down into a 0, just like that. Okay. And then the last entry, we have a sine squared. So sine squared, which is 1. 1 squared is just. Okay. So that's our element stiffness matrix for the first element. Okay. Any questions on that, how we got that matrix there? Okay. All right, so let's go ahead and keep going. Okay, so element B is actually the interesting one here because element B is not 0 and it's not 90 degrees. And so we actually have a lot to compute. And I usually don't like stopping examples midway, but I think all we'll have time for today is just writing out the element stiffness matrices, especially when we kind of cut it off before the weekend. But we'll come back on Tuesday and we'll finish up this exam. Okay, so element B. Element B, first, remember, we're going to pre-compute our sine and cosine, right? So the orientation for element B, let's go back up here. Element B is the one that's kind of pointing up and to the right. So the angle for element B is going to be 45 degrees. So let's go ahead and compute cosine and sine. So cosine of 45 degrees is root 2 over 2. And sine of 45 degrees is root 2 over 2. A 45, 45, 90 right triangle is one that was hopefully drilled to you at some point that's in your math education. Okay, so let's go ahead and write out or compute the element stiffness matrix for element B here. First of all, we have to take note of which nodes element B is connected to. So element B, let's go back up to the figure. Element B is connected to nodes 1 and 3. So that means our matrix here is going to be F1x, F1y, F3x, F3y is equal to. Now, element B is a spring, so we don't have AE over L in front. We just have the spring constant. And so our spring constant is 2.5 times 10 to the 5th. Okay. And this is going to be multiplied by our okay. So here our trick is going to be quite useful because we have, quite a few entries here. Okay. First thing I'll note is that, if you look at every entry in our element stiffness matrix here, it's the product of either cosine squared or sine squared. Okay. Just because we're going to do this over and over again, right? We're going to have a lot of instances where we're going to multiply root 2 over 2 multiplied by root 2 over 2. Okay. And so when you multiply two fractions like this, remember, you're going to multiply the numerators together. That's going to be your new numerator. Okay. So you have root 2 multiplied by root 2. And so the two roots are going to cancel out. Okay. So you end up with 2 up top. And then in the denominator, we have 2 times 2, which is 4. And so the result of root 2 over 2 times root 2 over 2 is just 1/2. Okay, so we're gonna have a bunch of 1/2s here. And we're in luck because both sine and cosine are equal to each other. And so actually, the only thing we have to really pay attention to is if there's a minus sign or not. Okay, so let's go through that first row. So the first row is cosine squared, cosine times sine, minus cosine squared, minus cosine times sine. Okay, and so we compute that, we get 1/2, 1/2, minus 1/2, minus 1/2. Okay. And then before we move on to the second row, let's do our trick. So let's go ahead and write this into the first column. Right, so the first column is going to be 1/2, minus 1/2, minus 1/2. Okay. Okay, second row starts with a positive sine squared, so that's going to be a positive 1/2. Okay. Next, and then we have two negative terms. We have minus cosine sine. Yep, minus cosine sine, so that's going to be a minus 1/2. And we have a minus sine squared, which is going to be a minus 1/2. Okay. So let's write those in. So we have minus 1/2, minus 1/2. Okay. Third row starts with a positive cosine squared, so that's going to be a positive 1/2. And then after that, we have a positive cosine sine, so that's going to be another positive 1/2 there. Okay. We write that into the corresponding column, so that's going to be another positive 1/2 right there. Okay. Right, and then the last entry in the bottom right is a positive sine squared, which is a positive 1. Okay. Okay. Good. All right, so we're just about. I'm not going to start element C. Yeah, if anything, maybe it's a good exercise for you guys to do before Tuesday. Maybe do this on Monday after you turn in the midterm project. Okay, but before Tuesday, let's go ahead and have you guys compute the element stiffness matrix for element C, and then we'll pick up from there with the assembly. Okay, so for element C, right, we're in luck because element C is horizontal. Okay, so that means the angle for element C is going to be 0 degrees. So that means sine and cosine are actually quite simple as well, okay? Because cosine of 0 degrees is 1, sine of 0 degrees is 0, okay? So we actually end up with a situation very similar to element A, where we're going to have a ton of zeros, okay? It's just that it's going to be shifted slightly because it's a horizontal element as opposed to a vertical element, okay? All right, so once you guys give that a try, of course, the answers for this are in the notes, okay? But then we'll pick it up on Tuesday. We'll look at the assembly of this example. All right, any questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for today. So thank you guys for coming today. Remember, midterm project is due this Sunday, so please make sure you guys get it in on time before the deadline. Please do that. Okay. I will be available tomorrow, mostly in the morning to answer questions. So if you have any last minute questions on your ANSYS simulations or on the report, definitely send me an email. I'll try my best to get through all of them tomorrow morning. Tomorrow afternoon, I'll probably have a bit of time, but I also have some family time tomorrow afternoon as well. But if you get it to me by tomorrow morning, I can guarantee I can get back to you before Sunday. Okay. All right, so thank you guys for coming. Hope you guys have a good weekend. Best of luck on the project, and I will see you guys next week. Thanks, Jason.
Have a good birthday party.
Thanks.